Before I begin this video, I must say I am not an expert. This video is more for my own education than for others, to work on developing my personal understanding as well as my teaching abilities. I highly recommend to continue and learn far beyond this simple introduction that I will lay out, but I do hope it will be a source of entertainment and intrigue. Symplectic numerical methods focus inherently on the structure and methods of Hamiltonian mechanics. Thus, to understand them, we must first understand why they are used at all. Because at first glance it might seem quite contrived. Hamiltonian mechanics is quite mathematically abstract and complicated. Beyond that, expanding it in different ways, such as dissipative or entropic spaces, require creative solutions. Thus, it begs the question, why is it such a developed field? The short answer is that Hamiltonian mechanic formalisms enforce energy conservation in a way that other formalisms simply don't. The long answer is, well, this video. First, a quick review of Hamiltonian mechanics. If you are comfortable, feel free to skip ahead. A Hamiltonian system is defined by the function h, the Hamiltonian, which represents something analogous to total energy. It isn't exactly, but for the purposes of this video, this definition will work just fine. In this equation, we have Q, which represents generalized position, which is the minimum amount of set parameters that fully specify where a system is in configuration space, where configuration space is a space whose points represent all possible configurations, meaning that generalized position is not confined to distance, but can also be things like angles, dimensionless quantities, or whatever other convenient quantities that can be used. The P represents generalized momenta, which holds the same rules position does, but represents momenta instead of position. The evolution can thus be derived that the derivative of position as a function of time is equivalent to the partial derivative of the Hamiltonian as a function of momenta, and the inverse, where the derivative of momenta as a function of time is equivalent to the negative partial derivative of Hamiltonian as a function of position. Here we can look at a concrete example, a simple pendulum. Such, one can take the partial derivatives to find that the derivative of position is equivalent to momentum divided by mass, which is exactly equivalent to velocity. Another can take the derivative as a function of momenta and find that it is equivalent to the force acting on the object. In phase space, the space of all generalized pairs, these systems trace out a trajectory. For harmonic oscillators, these are eclipses. Each eclipse corresponds to a different energy level. Here, the key points are that energy remains constant along trajectories, as trajectories are defined by conservative energy. The phase space volume is conserved, and finally, the most important for this video is that the Hamiltonian retains its symplectic structure, which is defined by the two form. Omega is equal to the derivative of position wedged with the derivative of momentum. To understand symplectic methods, one must first find their motivation. Why traditional methods fail in certain scenarios, no matter what type. To understand this, let's look at the simplest integrator, the forward Euler, where h is a time step. Let us apply this to our harmonic oscillator and see what happens. The trajectory spirals outwards. This is simply because the traditional methods aren't made to conserve energy. They aren't meant to model physics. The main reason is that tiny errors add up without the ability to contain them. Also, traditional methods add unphysical correction terms over time that lead to unphysical effects, being dissipative in certain areas and adding energy in others, adding artificial energy to the system in order to have temporary accuracy. Now obviously higher order correction terms help with these problems and make the models more physically help. But the problems are fundamental. Adding higher order corrections simply increases the computational workload without ever resolving the problem. Even sophisticated methods like the RK4 have this problem. It's accurate to the fourth order, but that means that the error per step is OH to the fifth, which is tiny but adds up. For something like a celestial simulation over millions or even billions of years, this creates distorted simulations. Symplectic integrators fix this problem by preserving the symplectic structure I mentioned earlier. The symplectic form is a mathematical object that measures oriented areas in phase space. For a simple system with 1 degree of freedom in both the position and momentum, each gains this equation. This is a 2 form. When integrated over a region of phase space, you get an oriented area or physical deformation. As the Hamiltonian flow evolves, the region over phase space gets stretched, rotated, and deformed, but the symplectic form remains preserved. From this basic axiom, one can derive something called the shadowing theorem that says, a trajectory computed by a symplectic integrator, while not exactly true, stays close to the trajectory of a slightly modified Hamiltonian. Meaning, standard integrators essentially create new equations that are close to the original. Symplectic integrators create another Hamiltonian that is exactly equal to the original Hamiltonian plus the order of the error. Such, the energy does not increase monotonically. It oscillates within a bounded region over exponentially long time. The error grows logarithmically rather than linearly. To compare, we must once again take the simplest possible case. Take the traditional forward Euler. Now turn to something called the backward Euler. Notice what has changed? We have updated momentum first, then updated position using the new momentum. One thing to note, backwards or implicit integration is commonly used outside of symplectic integration. It is also a general requirement for symplectic integration. There are special cases where explicit numerical methods satisfy the requirements for symplectic integrators. Another requirement being that it uses Hamiltonian or Hamiltonian-like formalisms. Now let's see why it's symplectic. We take the function where t is kinetic energy and v is potential. The symplectic Euler step can be decomposed into pure position steps, which is the flow of the potential, the pure momentum steps, which is the flow of the kinetic energy, the composition of the exact flow of the Hamiltonian, which is by definition symplectic. The exact requirements are quite involved and mathematically difficult to derive, so an independent video on this topic is required. For the purposes of this video, the general rules described and the types of integration are sufficient. Let's implement this for a harmonic oscillator. In this, the orbit remains stable. Energy oscillates, but doesn't drift. One can make the equation implicit by updating Q before P. The most commonly used symplectic integrator is the leapfrog method. It is second order accurate. The core idea of it is that it evaluates position and momentum at staggering time points. Think of it as a half step of momentum backward, full step of position forward. Using the half step, then the half step momentum backward again. This is symmetric. If you run it backwards, you get the exact same algorithm. This time reversibility is exactly what gives it second order accuracy. There is a compare the performance after 1000 orbits. For a time step of 0.01, forward Euler has an energy error of 15.3%, symplectic Euler 0.8%, and leapfrog 0.002%. As you can see, it's much smaller, as the error scales up by the square of the time step, allowing for larger time steps for similar accuracy. Derivation of this equation is outside the scope of this video, but an interesting idea that may be delved into in the future. To build higher-order symplectic integrators, one must first learn operator splitting. The key idea: if you write the Hamiltonian as the sum of two different Hamiltonians that you know how to integrate each piece exactly, you can build an approximate integrator by composing these exact functions of the two, where phi a is the exact flow generated by HA and phi b is the exact flow over HB. Then the true Hamiltonian flow is below the exponential of the Poisson bracket of H. The simple approximation is attained by composing the two exact flows. This is known as the Lie-Totter splitting. This method is first-order accurate. Higher-order methods can be built using splitting, such as the fourth-order Forrest-Ruth. A derivation of this is also outside the scope of the video, but is something we will get into.